Here we go. Hello, and welcome to the next lecture, Lecture 16 of Introductory Astronomy, the web course that's actually a real course being taught. A lot of students taking it for real credit. Many of them here at the same university, Michigan Tech, just aren't coming to lecture because they're on the web, as just discussing with the studio audience here. Though today we're going to talk about star death, in particular, stars that go boom, in some of the most tremendous explosions in the universe. We'll talk about tremendous explosions today. And there is a tremendous explosion in this galaxy, and we know because we took two pictures of it, and one of them has the tremendous explosion in it, the supernova in it, and one of them does not. So sort of like a Where's Waldo. See if you can find the supernova in these two images, and I will show it to you later in this lecture. Okay, first the obligatory slides in case someone has stumbled upon this and is clueless as to what is going on. This is Physics 1600 Introductory Astronomy at Michigan Tech. This is the 16th lecture on star death. Next time we will jump into black holes and see the fun stuff that goes on there. I am Robert Nemiroff, your professor here, professor of physics at Michigan Tech, and also one of the editors and writers for the Astronomy Picture of the Day, which is why we include that lots of images from APOD, as we call it, in these lectures. If you're taking it for credit, you need to know that you need to go to courses.mtu.edu. If you're not taking it for credit, then don't go there. That's the only way to see the quizzes. So I've now gotten several emails from around the globe, several, asking to see the quizzes. Now, one would think that you wouldn't want to take the quizzes unless you're taking the course, but some people, at least one person wanted to model the course for another class they're teaching, and other people just want to know what's being stressed and things like that. So I'm sorry, though, I can't open it up to you easily. So you'll just have to go without the quizzes for now. What are you responsible for in this strange video and computer age? The lecture material that I say, supposing it is correct. The listed Wikipedia entries, which I list every lecture. All the astronomy pictures that I posted during the semester. In particular, each week I review the APODs for the previous week. Keeping score, if I'm counting correctly, we have homework 1 through 7 already due, and homework 8 is due later today, and today is a Monday, by 5 p.m., I believe. Again, go to courses.mtu.edu to keep it all on one slide. Okay, first, there's a cool video that we posted on APOD last year that I could have put in last lecture, but I didn't think of it. So this is zooming in. It's good for astronomy to realize that many of the images we show you, I show you here and we feature in APOD, are just zoom-ins on the sky. Everybody kind of knows that, but this particular one shows it very clearly. This is the Astronomy Picture of the Day for July 2nd, 2007. And this will give you a total zoom from standing in your backyard, well, near a telescope dome, into the Pelican Nebula and the open cluster of stars that's right in it. So hopefully it's preloaded. So if I click on this, it will go relatively quickly. I don't know how to expand this to the full screen. I've tried to do that. Some allow you to do it. But here you can see, now we're going to be zooming in. This is the band of the Milky Way here. So we're going to go toward near the center of the Milky Way and keep zooming in on a reddish nebula there. There's the North American Nebula. This is the Pelican Nebula, and zooming in on part of the Pelican Nebula where there's an open cluster of stars. The big bright blue stars are the brightest, bluest stars in that open cluster. And here you can see one of these star pillars that we were talking about before. So I just think that's a really cool video to anchor what it is going on here. From if you had telescopic eyes, you can really go in and zoom in on these things. Usually, though, this is digital trickery. They're passing off to a more powerful telescope. In some cases, these zooms can include the passing off to the Hubble Space Telescope. You then match an image that doesn't have high resolution with a digitized version that didn't have the resolution, and then go zoom in on the highest resolution. So there you go. That was a part of today's fun. So we will minimize that. Oops, yep, go to the next one. Okay, so the Wikipedia entries for today will be stellar evolution, star death. You have to get to star death. You have to live a star life to get to star death. Planetary nebula, we'll talk about what those are. and why they have little to do with planets. A white dwarf, and why that's not a derogatory term. A supernova, big boom. Supernova 1987A, which is, you can get to on Wikipedia by SN 1987A, which was the first recorded supernova of 1987. SN is supernova, this is the year. A neutron star, that is something that you can end up with. That and a black hole after your star goes boom. Okay, in general, stars die in one of two ways, usually with one of three end products, or possibly four. If you have a low-mass star, and what is meant by low-mass star? Well, we're not exactly sure exactly what the dividing line is. It's a few solar masses, maybe on the order of 5 solar masses or so, M with an O dot. O dot is the sun sign. So this is 5 times the mass of the sun. Might be the dividing line between low-mass stars and high-mass stars. So if you have a low-mass star, of which the sun is clearly less than 5 solar masses, the sun is exactly 1 solar mass, the sun will not go supernova. So you don't have to buy supernova insurance. So the people who keep calling you, asking you to update your supernova insurance, just say no. The sun will eventually, in about 5 billion years, cast off its outer envelopes. And it is debatable, actually, whether the outer envelopes, when the sun moves to red giant phase, well, even before it casts off its outer envelopes, the sun will exhaust fusing hydrogen and helium in its core. And then it will start to, when that happens, the core will contract and become hotter and more dense. And then the outer envelopes will expand, and the sun will become a red giant. If the red giant envelope extends out past the Earth, which will happen in about 5 billion years if it happens at all, then the Earth will encounter a lot of friction and will be going through the outer part of the sun's atmosphere, a thick enough part of the sun's atmosphere, so that the Earth will eventually spiral in and melt. And this will significantly decrease housing values. There is unsure exactly how far the outer envelope will go, though. It's possible that the outer envelope will be inside the orbit of the Earth, still within the errors of the calculations. And if so, then we'll be right on the edge of a red giant. We'll be zipping around, and a lot of the sky, how the sun takes up a half degree in the sky now. In 5 billion years, it could take up like a lot of the sky, and we would be just zipping around near the outside. Experiencing more friction, running into more stuff, but we might then survive. After that, the sun might start fusing helium into heavier elements, including carbon, around the core, or inside the core. It could then undergo a helium burning and make carbon or something, and or a heavier element than that eventually in the core. Eventually, though, with a low mass, it's never going to have enough stuff pushing on it, outer envelope stuff pushing on it, to cause it to do more fusion. So it's going to end there. And then the outer envelopes of the sun will go off as the star contracts, and you're left with what was in the center. And what was in the center, which is circular, and although I can't make it here, is what used to be the center of the sun is a white dwarf. So the sun is destined to go and be a white dwarf. The center part of it, the sun, is going to be a white dwarf. The outer parts, for at least several thousand years, there's going to be stuff around it, and that's going to be a planetary nebula. And the sun is probably going to puff off its outer gases in several phases to create a planetary nebula that is not just a uniform sphere of stuff. So it's going to be somewhat complicated looking. It's possible the spin of the sun could be important in determining what the planetary nebula looks like. We're still learning a lot about what planetary nebula look like. The exact energy mechanism as to how the planetary nebula are expelled is still under some investigation. So if the sun has more mass than a certain amount, which I'll get to in the future, then it can even contract, it can even press on a white dwarf hot enough to cause things to happen, and you will not get a white dwarf in the center. Okay, so this is a famous planetary nebula. This is the Ring Nebula. And here, I believe, is the central white dwarf, or nearly central white dwarf. Sometimes pushing off the shell gives a little push to the central object, so it will drift off the center. But you're usually pretty near the center. So here you see there's hot gas. This is the outer envelope of that star. The ring nebula is actually not completely a sphere. One idea as to what the ring nebula might have been is it might be like looking at a balloon, a party balloon that's like blue. And if you look through it, you notice most of the party balloon around here. This is the densest part of the balloon, even though it's a sphere, the party balloon. And this part is the most clear. But it turns out that the ring nebula is actually more of a cylinder. So we're looking at a cylinder like this, and we're looking more down into the cylinder. So what has caused the ring nebula to become a cylinder and not a sphere is not clear. It could be the spin of the star itself. It could be a binary companion. There's all these little knots here, too, that are not all that well understood. I believe these stars are unrelated. They're just background stars that are around there. Okay, so the ring nebula is something you can actually see with a small telescope. It's fun to go out. And the zoom we just did on the Pelican Nebula, you can do the same kind of easy zoom to the ring nebula. Why are they called planetary nebula? Are they planets? Well, there could be planets near the center here, orbiting the white dwarf, that used to be a solar mass type star. But they're called planetary nebula not for that reason. They're called planetary nebula because particularly the ring nebula and others like it look a little bit like a planet on the sky with a telescope. They're angularly large enough so that they're angularly similar to some of the planets, although they're dimmer than Venus and Jupiter usually. But they're also somewhat greenish to the eye, sometimes a little reddish. But those things might be associated more with the colors of planets. So with early telescopes, not fully realizing that planets are all going to move with respect to the background stars, and planetary nebula is a background star and so won't. Looking at it, if you just looked at it over one night or 2 nights, you wouldn't notice that. You'd say, oh, look, there's a fuzzy patch, looks a bit like a planet. So they were originally called nebula that look like planets, planetary nebula. But they are not planets. They're not in our solar system. They're far away stars. Sometimes relatively nearby stars, but they're not in our solar system. It takes light at least several light years to get to them. Whereas in our solar system, it takes light like half an hour to get to the very outer parts of our solar system or so. This takes years to get there. Okay, here's an indication that here's the center of the ring nebula that we just saw right there. Ooh, let's change colors. I always want to do this. Let's go green. So there is the center. And if you had a deeper exposure with a wider angle, you would see that this star was busy doing other things here, even before. So these outer envelopes were thrown out first. So there was some process of this star that thrown out those outer envelopes, and only later did it create the more dense gas that we see as the ring nebula. This is a spiral galaxy, which is millions of light years away and completely unrelated to the ring nebula. It just shows that sometimes the sky is so packed full of stuff so that when you look at someplace, you find something else that is pretty cool. So if you get your telescope out and you see the ring nebula and you have a big telescope, you might look for this galaxy too. Okay. NGC 2440. Let's go back. Let's go to red again. So NGC 2440 is dimmer and smaller than the ring nebula in terms of angular size, but it's more in its early stage, apparently. Here we see a white dwarf or budding white dwarf, and you can see that the hot material coming off of that and the expanding material is moving away, so that this is a very young planetary nebula moving out from its star, and it's very complicated. It's not just a clean sphere. So this was taken by the Hubble Space Telescope. And this is a emerging planetary nebula. Okay, the Cat's Eye Nebula. This, I believe, is a white dwarf. This is a planetary nebula around here. This gets a lot of play on the web. Looks like an eye to some people. I get a bunch of emails having to do with some sort of some people attribute some sort of religious significance to this, and I'm not sure what that is. That's never been explained to me what that is. But every now and then I get an email from someone who's obviously interested in the religious interpretation of this, and I don't know that. It's a planetary nebula, as far as astronomy understands, with a white dwarf pretty near the center. Why it has these features, again, we're not quite sure. Ooh, let's go to blue again. We're not, go to blue. We're not quite sure why the details. A lot of planetary nebula details, how the stars throw out their outer envelopes, don't really know. But they do so many times in symmetric fashion. Here you can see this is somewhat mirrored by this is somewhat mirrored by that, this is somewhat mirrored by that. So, so there is some symmetry frequently, but not always involved in creating planetary nebula. Okay, so here we go again. Let's go to red this time, back to red. Hello? Okay. So this is the part you just saw right there. Once again, one of the neat things about modern astronomy is that we realize that if we take a much longer exposure, that more things come out. This is true on the amateur level, where amateurs are able to have these really cool, they just look with an average telescope, but they're able to track the sky from a dark location and see a wide swath of sky that the big professional telescopes can't track, because they're only looking at a really small part of the sky. Because the bigger telescope, usually the smaller the part of the sky you look at. But with the smaller amateur ones, they can look at a big part of the sky, and since they can now have sensitive CCDs, they can now track the sky, they can just build up an image over a long period of time. So in that spirit, this image was taken, a very deep image of the Cat's Eye Nebula, and here you see there's all kinds of fun stuff going on here. And there's all these shells and things. So this star had a complicated history of throwing out its outer envelopes. Oh, this was a Hubble image, though, not a home-based image. And now this is not the Hubble Space Telescope, this is ground-based. So yes, but can your telescope do this? So here is what we saw before. And now with an even deeper image, you can see this star was up to no good even before that, throwing off lots of strange appendages, not very dense gas and dust. So did its stellar wind thicken? Did it have some kind of event where it fused briefly and contracted and had a high opacity event to throw stuff out? Was there some kind of explosion? Not really known. Okay, here's a clearly, it's called a bipolar planetary nebula, M2-9, so you need a telescope to see this. I think this is, this is Hubble Space Telescope again. So here's the center star. I think it's stars in this case. To create something like this, with this kind of symmetry, usually requires a binary system. So this is the star that underwent the planetary nebula phase was a relatively low mass star, but it probably had an even lower mass star that had not yet evolved orbiting it. And so the orbiting plane would be right here, and these things would be perpendicular, sort of like jets coming out of the orbital plane. Okay, this is more of a spherical nebula, but not completely spherical. It has an inner part. It also has a tremendous tapestry, like a spirograph pattern, so it's called the Spirograph Nebula. Now, when I was little, I played with spirograph. I don't know if they're still common toys. Who here in the studio audience has played with the spirograph? Who knows what it is? Okay, we're at 50% here. So a spirograph, not an advertisement, was you had a circular thing that had little teeth on it that went around it. And then you had, you could take out of the box any number of circular things like this and put them down. And these things had teeth on them. And these teeth would lock, which means that this guy could roll on there. And then what you did is you put your pen in here and you let it move around. And when that happened, you got this spirally pattern that was really cool. And then you could say, hey, Mom, look, this is really cool. And she'd say, oh, that's so nice. And then what you could do is you then put your pen in another place and move it around. You get another spirally pattern. Then you can get a bigger wheel, and you lock that in. And then you can get just something that you can build up a very sophisticated pattern of loops with just a pen and some plastic. So this nebula looks like there's all kinds of loops or something going on in there. So it looks like it's called the Spirograph Nebula. Again, taken by the Hubble Space Telescope. What is the physical process that creates that texture? Don't know. This is the kind of image, actually, that once made a really great astronomy picture of the day, but it doesn't expand well. So when you take a higher, it turns out that the fuzziness here is intrinsic to the nebula, so far as I can tell. So when we take a higher resolution version of this, it becomes fuzzy. whereas at a lower resolution, you could just about see the fuzziness and say, oh, that's cool. So some nebula expand well and some don't. But it's still a very cool object. Eskimo Nebula, really interesting. Another planetary nebula. Again, not quite sure. Here's the neutron star. No, I'm sorry, here's the white dwarf. Let's go to blue again. Right in there. How it created, this thing seems to have unusual structure. To the first thing, it looks sort of like a heart or something. It kind of looks like an Eskimo with a parka on to some people, which is why it's called the Eskimo Nebula. Although a Cyclops Eskimo, I guess, with the one eye. What symmetry could give that? Not quite sure. Again, you have these things that you see in the Ring Nebula. These are knots of gas that were, I guess, the outflowing gas isolated these knots. Why these knots existed, don't know. Do these knots like that, knots of high-density gas, exist in our own solar system? Maybe. Maybe they're related to comets or something like that. Maybe not, though. But maybe there's these just denser knots of gas out there that we don't see. Now, they'd be head-on to us if we were in the center of this and we looked out, at this thing. We wouldn't really see it very well. We don't have a good way right now of mapping out the knots of gas that would exist in our own solar system. But looking at other ones, they seem to be isolated by the planetary nebula process, in particular the early gas that comes out tends to stratify them. So in the center is a white dwarf. So what is this white dwarf? Well, white dwarf, I like to say, has two common attributes that aren't usually associated. One is it's got the mass of the sun, which is good because the sun has the mass of the sun. The other is it has the radius of the Earth, because it's good because the Earth has the radius of the Earth. The strange thing is it has the radius of the Earth and the mass of the sun both at the same time. So the sun is much bigger when it has the mass of the sun. So if you could picture taking the sun and squishing the sun down to the size of the Earth, then you would get something that would have the mass of a white dwarf. The white dwarf is held up by something called electron degenerate pressure. Which is different from, let's say, a normal star is held up by just gas pressure, which is the heat of the gas itself as the molecules moving around, the atoms moving around so fast that it holds it up. There's also fusion that goes on, but there's no fusion going on in a stable white dwarf. What's happening is that the electrons have been pushed together. And there's protons there too, so it's not just electrons. It's not this highly charged object. No, it's electrically neutral, so there are protons in there. But there's lots, the electrons are the easiest to move around and the fastest to move around. So if you try pushing lots of electrons together, you find at first that they want to move together like any pieces of matter want to move together. After a while, they want to electrically repel because they're all negatively charged. But if you sprinkle enough protons around there, then it doesn't matter anymore. So they're not electrically repelling anymore. But then you run into something that's similar to what happens in atoms. In atoms, you can't put another electron in the lowest state of the hydrogen atom. So you have in a hydrogen atom, you have a proton, and you have an electron surrounding it. And it's in that shell. If you were to put another electron in, it would be further away. So there's something called the Pauli exclusion principle, which is a principle. Well, it's actually interesting as to what causes electron degenerate pressure. What causes the Pauli exclusion principle is actually somewhat debatable, but it is an observed physical fact that electrons do not want to be in the same physical state. They just don't want to. They can't do it. So when you get down to that amount of physics, when you get down to that kind of densities, where you're trying to push them into the same state, sometimes in a hydrogen atom, so it just doesn't happen in a hydrogen atom, but in a white dwarf, you're trying to do it, but they don't want to go. So that actually results in a pressure, and that pressure is called electron degenerate pressure, of electrons not wanting to be in the same state. Stop this. Don't push us more together, they're saying. And you get this really dense, relatively uniform density object. Okay, so the escape velocity from the surface is about 0.02 times the speed of light. White dwarfs can interact. there are known and hypothesized white dwarf binary systems where two white dwarfs might merge. So the question came up many years ago. What would happen if you kept dumping mass onto a white dwarf? Or let's say you had two white dwarfs that would collide. Let's go to red again. So these white dwarfs are going to collide. Is there a limit past which electron degenerate pressure will not keep these things up anymore? Well, even though we don't really know the detailed physics as to what causes electrons to not want to be in the same state, we do know that you can push this to some limit where even in those approximations, they're at zero radius. And so when that happens, you go over some limit, and that's called the Chandrasekhar limit, which is estimated to be 1.4 times the solar mass, is the Chandrasekhar limit. Once you have a white dwarf above that mass, then electron degenerate pressure isn't going to work anymore. It would essentially be zero radius again. And so what happens is the electrons get pushed into the protons that are around, and you get lots of neutrons. So once you have all these neutrons, the question comes up, well, do neutrons ever want to be in the same state? And the answer is, well, no. Neutrons are also of the type of particle that don't want to be in the same state, called fermions. And so you have a new kind of pressure of neutrons not wanting to be together, and that's called neutron degenerate pressure. And something that's held up by neutron degenerate pressure is called a neutron star. Okay, so let's go. So we'll get back to that, neutron stars, in a bit. Let's first finish up the white dwarf stuff. We've seen this picture last time. This is an intermediate polar, where here is a star that is dumping mass onto a white dwarf. This white dwarf here was a normal star. It then threw out its outer envelope, maybe showing a spectacular planetary nebula. So then this white dwarf has a magnetic field, so this magnetic field is holding up the material for a while, but every now and then the stuff falls on here. And so matter accumulates on the white dwarf. If the white dwarf ever goes over 1.4 solar masses, then you're going to get a big boom. But it turns out that you can get a small boom if you just gets hot enough on the surface of the white dwarf to fuse hydrogen to helium on the surface of the white dwarf. So previously, the only time we ran into fusion was in the centers of stars in astrophysical contexts. But here we've come into a case where it's so hot on the surface of a white dwarf that this hydrogen that's being dumped on there might be so hot that it fuses into helium right there. And then you get something called a nova, which is different from a supernova. Nova. So here's another artist's rendering. These are not pictures. Although they're astronomy pictures of the day, they're not photographs. They're artist's illustration. There's stuff spiraling onto this white dwarf. Becomes regions so dense and hot and hydrogen on the surface that there's a thermonuclear explosion, and this stuff gets thrown out. But a thermonuclear explosion might be enough to devastate a city on planet Earth, but it's not enough to detonate your average white dwarf. So the white dwarf is going to survive that. It might disrupt the accretion disk here. So the accretion disk needs to reform from this material coming off this star. That might happen. But it won't usually destroy the white dwarf. But what you will see is this little bit of light here. About once a year or so, maybe about once a year, a nova becomes bright enough to be seen by the unaided eye. Now, most of these are not spectacular to see. They're not like comets. So they're not all that well recorded. Many of them are missed because we still don't track the sky completely even down to look for changes, even down to human eye visibility. But here you see someone looking closely toward a nova. And it's not that spectacular to see usually. It just looks like a star. But what's interesting about it is that it wasn't there, last week. And it can take a nova, a month or two to fade, and it won't be there again. So it's like a guest star. It was there, and it's gone. But the neat thing about nova is they usually recur. So if you wait long enough, sometimes it's longer than human lifetime, so don't buy too much popcorn and sit there. But if someone, and a group of people, tradition of people, culture of people wait long enough, that white dwarf may recur, and there might be enough hydrogen built up on the surface of the white dwarf to create another thermonuclear explosion, to create another thing that we can see. Okay, this was an unusual event that is thought to be possibly nova-like in occurrence, and the surface of this star V838 Monoceros, which tells you the constellation. So this star became much brighter. Actually, and so the light that went out then started reflecting off of the dust that was around here. So what you see here is dust, and it's reflecting the light. And as the light goes further out, it's reflecting off of dust that's further and further away from the central star. So previous back, you can see as time went on, and this time is only years, the expanding, you're not seeing an envelope expand. You're just seeing light reflect off of more and more distant dust around, gas and dust around this star. Okay, so we can see lots of white dwarfs if we know where to look by themselves, behaving themselves. So the Hubble Space Telescope here looked at a globular cluster M4. So M means it's bright enough you can see it. So here it is, globular cluster M4. Stars, stars, and more stars, as you know for globular clusters. But what you usually see, well, in globular clusters, you don't see the big blue stars because they don't have the big blue stars. The brightest stars they have are the red stars. But even dimmer than your average red star is there's many white dwarfs in globular clusters. And so they're able to, by their brightness and temperature, they were able to pick out which ones were the white dwarfs. And here is one right there, pointed to by the arrow. So here's another one. This is, I guess, a globular cluster, and there's lots of white dwarf stars here found by the Hubble Space Telescope. Relatively old picture. Okay, so now we're going to move into another realm of something that's not a nova. It's brighter than a nova, much brighter than a nova, and so it's called a supernova. And so here we see a distant galaxy, a faraway galaxy, not unlike our own Milky Way galaxy, and on the outskirts of this galaxy, there's a point of light that appeared and then disappeared. And if this happened at the distances of the nova that we see, it would have been tremendously bright. Might have even affected life on Earth. You could be able to read by it. So it would be dangerous if it happened too close. But in this distant galaxy, it's, again, a point of light that brightens. You could see it with the telescope. This one I did not get bright enough, I think, to see without the telescope. But it was an indication that there was something tremendously violent happening out in the universe. So we see in distant galaxies a supernova occurring every 50 years or so on the average. So if we keep watching this galaxy, as 50 years go by, we'll see another supernova somewhere. It won't be the same place because that star is gone. If it was the same place, it couldn't have been a supernova. A star can't go supernova twice. That's the end of the star's life. But over here, there could be one, or this is probably a foreground star. So every 50 years. Strangely enough, there hasn't been a visible supernova in our own galaxy for a while. And it might be because it's hidden by some of the dust. It could be far away. But it is a little bit strange. There hasn't been one that we could see relatively nearby. However, there was one in 1987 in a neighboring galaxy, in the LMC galaxy. There was 1987A, so we'll get to that. Now we're back to searching for supernova. This was the quiz at the beginning. Here we see a spiral galaxy. M51, I think, actually shown several supernovae in the past 10 to 20 years, more. So if you think it's this, no, that's a red nebula, and you can see it there. If you thought it was this, no, here's one over here, although it might look a little different. Does anyone know where it is? Is anyone in the studio audience able to find it? Where? What? Okay, if this is a clock dial, where on what time on the clock dial would it be?
Just south of the center, so 6 o'clock.
6 o'clock, so that's correct. Okay. Did you see this before, or did you just find it? Okay, just found it. Okay. So it's at 6 o'clock. So 6 o'clock is down. So if we look down here, we're looking for it. So I'll look in this area here. There, see it? Now hopefully everybody sees it. It's right here. And there's nothing that bright on the other side. So there's lots of interest in finding supernovas these days because they help calibrate the distance scale of the universe. They help tell us that a certain type of supernova is called a standard candle. And so a standard candle means that it can be calibrated all to the same brightness, and therefore we can see how bright it appears and how bright it really was, and then we can see how fast the universe is expanding and what might be in the universe to cause it to expand like that. Okay, so supernova. So it is possible for a white dwarf to go supernova, and those tend to be somewhat of the more interesting type. So if you have a supernova that's a white dwarf that's part of a binary system, and it's getting too much mass dumped on it, and it's not able to nova it off fast enough, then it goes over the Chandrasekhar mass and becomes a supernova. And those supernovae are thought to all be pretty much the same. And so therefore, these type 1a supernovas are pretty much standard candles. And they're very useful for calibrating the universe. Other types of supernovas are very common too. Type 2 supernova involves fusion in the cores of stars more directly than the type 1a's. So with the sun is currently happily burning hydrogen to helium in its core. For a very massive star, greater than about 5 solar masses, but that number isn't all that well known, it's then going to easily start fusing helium into a higher element in the core. And that's going to give a lot of energy out too. Helium's going to become carbon. And then the carbon's going to start, after that's done, then in the very center, it's going to start fusing carbon into even heavier elements. And then it's going to start fusing that into even more heavy elements. And these phases actually all last much less amount of time than the hydrogen burning phase. They can last only 1 million years or so. But then you get to iron. Eventually, your core is made of iron. And then you contract and you try to fuse iron. But the problem with that is iron is, in some sense, the most dense nucleus. You cannot fuse. If you fuse iron, you're not going to get energy out of it. It becomes endothermic. It takes energy to fuse iron. It doesn't give energy. So when that happens, you then get an energy sink, and the core keeps collapsing instead of providing enough energy and pressure to hold up the star. And then as that core collapses, for some reason we're not sure, it bounces typically. Or if it bounces, then you get a supernova explosion, a type 2 supernova explosion typically, and all kinds of elements are just released in a tremendous flare that lasts days. The neutrinos come out actually in seconds. And you're left with either one of two cores. The iron core will then have transformed itself into a neutron star, possibly. Or you could have created a black hole if it got too dense. It is thought that there's another limit past 5 solar masses that may be 10 to 15 solar masses. Let's put 15 solar masses, but I don't think it's key. The exact number is not important because we don't know it that much. Above that mass, it might get so dense that you get a black hole. And maybe between 5 and 15, you get a neutron star. There's lots of computer codes to try to compute this. Many of them don't get a supernova explosion at all, and they have to put in sometimes what's called a tooth fairy in order to make it expand. You have to put in an assumption that it will bounce or something to get it to expand. What happens during a supernova explosion is amazing in the sense that all of these higher elements, before supernova explosions, the universe is pretty much hydrogen and helium with trace amounts of other elements. With a supernova, all that fusion that was going into heavier elements, those elements all come out now. And not only that, but during a supernova, you get creation of elements too. So the supernovas release elements, heavier elements they've been created. Well, who cares if they release heavy elements they've created? Well, we're made of those elements, most likely. Much of what we are, particularly around the carbon range and things like that, has been released in a supernova explosion. So the famous quote from Carl Sagan that we are star stuff, that's partly what he means. The heavy elements that we are were created were created or released in supernova explosions. Okay, so here is the winner of the contest for brightest supernova yet found as of 2007, I believe. So here you can see most supernova images are not as spectacular as the ones I've been showing you. This star here now shows a little bright appendage, and so you can zoom in on that with your telescopes and determine what type it is. This is the mess that is left when a star explodes. This is the Crab Nebula. The Crab Nebula exploded in 1054 AD. That's one of the few we know. The exact date, it was recorded by Chinese astronomers and possibly by some Anasazi, I think their names is Indians of the U.S. Southwest. But today we can see the expanding envelope of the supernova. the supernova remnant. In the center, there is a neutron star pulsar that is spinning, and we can see the pulsar. And it is spinning, I think, at 3 times a second. And this image is a conglomerate of many different types of optical images. In the center, you see ultraviolet and X-ray images of the center region. This is a supernova remnant. So the supernova remnant itself begins to glow in other things. This is a pretty spherical explosion. Well, it wasn't spherical in the outside, but then after it expanded enough, it probably became spherical, mostly spherical. We see it glowing by the heavy elements that are decaying. So it created some heavy elements. These heavy elements decay, and they emit light, and we see that light. Some of these are radioactive elements. Some of them are just decaying. Here's another image that shows a more complicated structure, Tycho supernova, observed by Tycho. This is in the X-ray range that we're seeing this. In the optical, you can see many of the filaments left over from a supernova. This is Siemens 147, it's called, supernova remnant. And it's these red filaments that are the supernova remnant. Supernova 1987A was seen here on Earth in 1987. Technically, it must have occurred something like 50,000 years before, because we only saw the light from it in '87. It shows that we don't understand supernova. Even these rings that were then seen shortly after the supernova, not well understood why they're there. This is something more expected, the shell of a lit shell of the supernova, and there is an expanding shock wave that goes out that just has reached this to light that up. We'll see that in a bit. This is, I believe, an unrelated star. Why these rings are probably emitted before the star went supernova. Whether this is part of a binary system or not, why these rings existed, I'm still not sure. Okay, so this is you can see the expanding shock wave from, I think, 1987A. Here in differences images, all the stars get subtracted, and the shock wave is more easily visible. Okay, here you see a part of the shock wave hitting an existing shell that was already out there and lighting it up. Here's something interesting. Something called Schur 25, the 25th element. Let's go to blue here of this list. Here is I think, an open cluster of stars. This star is interesting because it seems to be showing shells similar to supernova 1987A, but it hasn't gone supernova. So maybe this thing is setting up to do the same thing, and so this has become one of the better candidates for supernova. So some people are keeping their eye on Schur 25 to see if it's going to explode. Eta Carina in the southern hemisphere for a while became, I think it was the second brightest star in the sky. And now it's faded to, I think, still naked eye visibility, but just not particularly bright. So Eta Carina is in the middle of this. And it's created this amazing envelope of dust and jets coming out. And we watch this, and this star will probably go supernova maybe in the next 1,000,000 years, maybe less than that. So people think that if you just sit there, some people might be under the impression that if we just sit there and watch, these stars are going to go any minute. But things happen so slow on the stellar timescale, usually, that fast on the stellar timescale is 100,000 years. We don't know. We watch 100,000. If we had 100,000 stars that were in this stage, we could watch them and one would pop off next year. But we don't know that many. We only know a few. So it'll be a while before it goes. Okay, a neutron star, as I said before, is held up by neutron degenerate pressure. These are neutrons that are not wanting to be in the same state. These neutrons are found by their pulsar nature. They were predicted to exist earlier on by people such as Oppenheimer, who helped create the atomic bomb. But they weren't found right away. Were considered to be fanciful for a while. And then pulsars were discovered, these flashing things that flash several times a second. And the original interpretation for pulsars were little green men civilization trying to contact us. But that quickly fell away because all they were telling us was beep, beep, beep. You know, it was kind of boring. And that's a more complicated explanation. So it was easily explained by going back to these neutron stars that were hypothesized and considering them to spin around a spin axis, which worked really well. And so very quickly after pulsars were discovered, it became the leading model was neutron star spinning. And so that's what we still believe today. So here's a neutron star here. There's a magnetic field here. There's things moving on the surface. A beam of light comes out on the axes, and if we're in that beam, then we get to see the optical flashes. Broader, so here's a composite image of the Crab Nebula again. This I think I've shown already. Broader than the optical beam is the gamma ray beam. Gamma ray, so it's easier to be in the gamma ray beam than the optical beam. So we've actually found one since this course has started. It's been reported. A gamma ray, it's called a dark, we've dubbed it a dark pulsar, where you don't see the flashes in the radio, and that's where the pulsar was originally discovered, and in the optical, but you do see them in the gamma ray. And that does make sense if we're just out here in the gamma ray range, seeing those, but not in the more narrowly beamed optical range. So here is a lonely neutron star. Not all neutron stars we see are as pulsars. Now that we know what to look for them, we see, dense, hot objects out there, and the best guess for what they are neutron stars. So here's one that's not doing anything spectacular. Okay, so it looks like I'm going to end a little bit early today. Back to the original phrase, the original image as to identifying this. Supernova, as I said before, are more interesting than just spectacular explosions. They help us determine what the universe is because we can see them. They are such spectacular explosions that we can see them across the universe. We can see them far away, and then if we can find supernovae, which we have found, that are roughly the same brightness, we can find out how the universe is expanding and what its composition is, and we will talk about that in future weeks. So until next time, we'll talk about black holes. I'll see you then.